Up until this point, we've been working a lot with triangles. We've been solving parts of triangles, and more specifically, we've been solving parts of right triangles. With right triangles, you know that you have the ability to use either the Pythagorean theorem to solve for sides, or if you're trying to solve for angles, we have the trig ratios. We have SOH, COH, TOA. But the question now comes into play, if we don't have a right triangle, how exactly can we find the parts of those triangles? And so that's what we're going to be looking at today. So if you take a look at this diagram here, you'll notice that we have a triangle. It is not a right triangle. Now we have angle A, angle B, and angle C, and they are not right angles. But what we can do is we can draw an altitude, a height, directly straight down from its highest point, the vertex, right at B, straight down, and you'll get a right angle there. So what we have created there is a right triangle. And by using some right triangle trigonometry, we're able to find the parts of basically what you see here, a non-right triangle. So if we take a moment and focus on just one angle, let's say we focus on angle A, and we would think about the trig ratios that we already know. We know that sine of A is made up of, sine is opposite over hypotenuse. So sine of A would be the same as h over c. Now if we do the same thing with angle C, let's focus on angle C now. So angle C, if we do sine of C again, we have opposite over hypotenuse, or in that case that would be h over A. Okay, so if you notice for each of these ratios, if we end up solving both of these ratios for h, what we end up getting is that h is equal to c sine A, and also h is equal to A sine C. Now, with that in play, what we can say is because they are both h's, just substituting one h for another, we can say that c sine A equals A sine C. And if I just divide both sides, let's say that I divide by A, right? And then after that, I then divide by C. Imagine doing that. What you'll end up getting is the result of sine of A over A is equal to sine of C over C. Okay, you'll notice that this is actually a capital letter on top, right? The angles are capital letters, and the side lengths are smaller letters, lowercase letters. Okay, so what we have just developed right there is a way in which you can use angles and sides of non-right triangles to find missing parts of that triangle. Now, as it so happens, if you imagine taking this triangle and maybe rotating it, what we can do is just rotate that triangle around. Imagine we were to rotate it, let's say counterclockwise. And so what I'd end up seeing there is that angle C would now be on top. Angle B would now be to the left, if you just imagine it being rotated, right? And angle A would therefore be on the right. So something along the lines of like this, right? Now remember, any triangle can form the height by going from the highest point straight down, and then you can create an altitude that way. Now, as it so happens, if we do this, if we classify the sides as well, remember that the sides are basically just the same letters opposite its angle, so this will be side C. Over here we have side B, and over here we have side A. Okay, so they're always opposite each other. But if we do that, if we go ahead and establish again the idea that what we drew there was the altitude or the height, then we can call this h again. And we can do another set of proportions where, we now focus on angle B and angle A. Okay, so in doing that, let's say I want to focus on angle B. What I see here is that with angle B, I can create another trig ratio of saying sine of B is equal to opposite over hypotenuse, and sine of A is equal to opposite over hypotenuse. Okay, and in doing that again, if I solve for h, I see that h is A sine B, and here we have h is B sine A. And then, since they're both h's, I can set them equal to each other, so therefore I see that A sine B is equal to B sine A. And just like we saw in the previous example, if I divide both sides, let's say by B, and then divide both sides by A, then what I end up seeing is that sine of B over B is equal to sine of A over A. Oh, and if we actually combine that, with our property we saw above, what we know is if sine of A over A is also equal to sine of C over C, this is basically creating what we call the law of sines. And so if you look up above, the law of sines says that the sine of A over A is equal to the sine of B over B is equal to the sine of C over C. This is our law of sines. And this basically, these ratios or proportions allow you to find the missing parts of non-right triangles. Also keep in mind that the sum of all triangles, the sum of their angles, is always 180 degrees. Okay, so those two properties right there will allow you to find missing parts of triangles. Okay. Oh, one more thing before we end this video. As we take a look at the next page, you'll notice now that we have an obtuse triangle. Unlike the previous one, you can kind of see that that wasn't a acute triangle. If you have an obtuse triangle, things don't change. You can still use the law of sines, where we say sine of A over A equals sine of B over B equals sine of C over C. Now, why does this hold true? Well, if you think about the sine of A, if we think about what sine is equal to, remember that sine is opposite over hypotenuse, but in this case, we don't really have an opposite, or hypotenuse rather, that you can use because there's not a right triangle there. But the law of sine still works here, because if you think about how you can find equivalent sine values, remember in a previous lesson how we had seen that the sine, or basically the y value that's in quadrant 1, is the same as the sine in quadrant 2. So because they have the same value, remember that sine is both positive both in quadrant 1 and quadrant 2. They are both going to give you equivalent values. So let's say we have a sine of 30 degrees, right? That's the same as the sine of 150 degrees. So the obtuse angle is going to actually give you the same measurement. So that is why you can still use the law of sines with obtuse angles. Okay? And that'll conclude our video for today.